So now we look at equilibrium, and we'll have to see what we mean by equilibrium. So this is can be defined as a condition in which an object is in equilibrium if its acceleration is equal to 0. That is, it has no acceleration. So an object that has no acceleration is in a state of rest. It is in equilibrium. Now we can have two kinds of equilibrium. If the velocity is also 0, okay, a is 0, that it has to be. If the velocity is also 0, which means it's at rest, this is called static equilibrium. Static means not in motion. And if the velocity is not 0, that means it's moving at a constant velocity. This is called dynamic equilibrium. Now, for engineering courses, there's a course called statics. Okay, it's called statics. Okay, and that deals basically with static equilibrium. And there are also a whole course on dynamics, which would deal with dynamic equilibrium. So I think the static equilibrium course will be compulsory for most everybody. So now if an object is in equilibrium, so if we want to write the sum of forces equals ma, and it's in equilibrium, so a is 0, so this equation would become the sum of forces is 0, because a is 0. And this can be broken up and written as sum of forces in the x direction is 0, the sum of forces in the y direction is 0, and the sum of force in the z direction is also 0. And this collectively becomes the first condition of equilibrium. We'll see the second condition of equilibrium in a later chapter. So now we'll do some examples on equilibrium, and we'll also do some examples which are not in equilibrium and they do have an acceleration. So now let's consider an object on a table. And here's the ground. The table is here. And we have an object, and in the book this is a computer monitor sitting on the table. So its acceleration is 0. The object is just stationary. Its velocity is also 0. So it's in a state of static equilibrium, which simply means the sum of forces has to be 0. Now we need to see what are the forces acting on it. And the first force is the force of gravity. So the gravity, which we write as Fg, force of gravity, that will pull straight down towards the center of the earth. And because F equals ma, this becomes equal to mg. So that is also called the weight of that object. So the weight of an object is m times g, and g is 9.8. Now if this were the only force, this object would have to accelerate downwards. It would be in a state of free fall, accelerating at 9.8 meters per second squared. But it's not. That means there must be another force that's exactly balancing this force, so that the sum of forces is 0, and so the acceleration is 0. So that force is, it has to be this way, exactly opposite in direction and equal in magnitude. We call that n. And n is the normal force. Now, normal here doesn't mean being something that's not abnormal, but it means something that's perpendicular. So normal in physics means perpendicular. So this is the surface, and the normal force is perpendicular to the surface. Normal force is always perpendicular to the surface, so let's add that. So that's the normal force. Now we'll write the condition of equilibrium. So if this is our x-axis, this is the y-axis. Normally the y is vertically upwards and the x is horizontal. The z would also be horizontal. Then if you write the sum of forces in the x direction is 0, well, there is no force in the x direction, so there's nothing in here. This equation gives us no information. The next equation would be the sum of forces in the y direction is 0. So we look for all the forces in the y direction, and we see that we have in the positive y, we have the normal force, so we can just write it as plus n, or just n because it's positive. And the fg or mg, which is negative because it's acting downwards, and that they equal to the right hand side, or you can say they equal to ma, and a is 0, and therefore the normal force is equal to fg, which is mg. So the table is pushing upwards with a force that's equal to the weight of this object. Now, the normal force is not always mg. Sometimes it's more, sometimes it's less. For example, if there was a person who would push it down, so you have a person's hand coming here and pushing downwards, then with a force, let's say F, H, and now we find the forces. So the sum of forces in the y direction is 0. We have the normal force upwards, the mg downwards, and also this F with the hand pushing downwards, and therefore the normal force is mg plus h, fh. And so the table has to push upwards, not only to balance the weight, but also the force being exerted downwards. If the table cannot exert that much force, this thing is going to go through. It's going to break the table. Okay, so now let's solve more problems. I will do several examples using this, and the first one is that if we have a solid surface here, and we have two strings tied to it. I'll just take the same numbers as we have in the book. So one string is at 37 degrees and the other is at 53 degrees, and then together here there's another string and there's a traffic signal that hangs from it. And the question is, if this is 1 and this is 2 and this is 3, what are the tensions in these cables if you know the mass of this traffic signal? Now we need this kind of to solve this kind of problem in order to find the tensions in 1 and 2, so that we can design appropriately and have a sufficiently strong cable here that can withstand this this tension. We don't want it to break. So now the first thing we need to do here is make a free-body diagram. A free-body diagram is a diagram that involves or shows all the forces. So, and this is a rather important thing to do in these problems. Normally, we consider objects to be point masses, so the whole mass of this object is concentrated in the center, which is called the center of mass. Along each string, there's a tension that pulls in both directions, so we'll have to see which one to consider. And then third thing we need to do is to break up all the forces in x and y directions, and then write the equilibrium equations. So in this case, we have, let's draw it here, we have at this point, we have a T1 this way, that's the tension in this cable, and then we'll have a T2 tension in this cable, and we'll have a T3 excuse me, tension in this cable, which is pulling downwards, and this is pulling up, and this is pulling up. At this point, the cable is pulling whatever is tying over here is pulling it downwards, and the tape is pulling downwards over on this roof here, but we are not concerned with that because we want to find these tensions, so we consider this thing. So this is one figure, and the other is for the mass. So this mass has an mg pulling downwards, that's mg, and this tension T3 is pulling the mass upwards. So T3 is pulling this knot downwards, and T3 is pulling this mass upwards. And the value of T3 and T3 is the same in magnitude. Now we write the sum of forces. So first we look at this one. We say, well, there's no Fx, so we just skip that. Sum of forces in the y direction equals 0. We no need to write ma. A is 0, so it's just this. And this is equal to T3 upwards minus mg downwards. And therefore, we get the result that T3 equals mg. So we have one answer. We have the tension T3. Now, a first thought might be that T3 is going to be T1 plus T2. Well, in vector form, yes, T3 vector equals T1 vector and T2 vector, but in terms of magnitude, T3 is not equal to T1 plus T2. So now we write the equation for here, but we need to break the forces up into x and y directions. So we'll break this into an x component. So let's do it with this color. So the x component is T2x, and its y component is T2y, and the x component of T1 is T1x and T1y. So now we write the sum of forces in the, let's say, x direction first. So in the x direction we have T2x minus T1x. So T2 is to the right, so it's positive. T1x to the left, T1x to the left, so it's negative. And they equal to 0. These are the only two forces. Well, T2x, this angle is 53 degrees. So this is, if you draw a line here, which is the x-axis, these two become parallel lines, and when a line crosses two parallel lines, this angle becomes the same as this angle. This is also 53, and the same here, so this is also 37. So we have this as 53 and this as 37 degrees. And now the T2x is going to be T2 cosine of this angle, and T1 is going to be cosine 37. So we know the cosine, so we have another equation. And now we write the sum of forces in the y direction is 0 for here, and we have two forces going upwards and one force going downwards. So we have T1y plus T2y, both positive, and T3 negative equals 0. T1y is going to be T1y is going to be T1 sine 37, and this is going to be T2 sine 53 equals T3, and T3 we have from here, it's mg. So we have one equation here, one equation here, two equations and two unknowns, T1 and T2. So solving these two simultaneously, we can get the values of T1, T2, and we already have T3. So we can calculate and get all the tensions. Now, one of the things that you might ask is, when we're in this case, when this angle is 37, why didn't we use this angle, which is 143? We should have used this angle instead of this one. Well, you can use this angle and say it's going to be T1 cosine of 143, which is the same as negative of T1 cosine 37. So either use minus T1 cos 37 or use T2 cos 53, which is the first one, plus T1 cos 143. And this plus T1 cos 43 is the same as minus T1 cos 37. Ultimately, you know that this whole thing has to point to the left. So that can guide you how to do this. Or you can break the whole thing into I and j components, write it as whatever I and then j, and you'll get, well, this would both be I. So one will be plus I, the other will be negative I.